Hello everyone. In this lecture, we are going to see about filter implementation in RF transceivers. Filter designs beyond 500 MHz are difficult to realize with discrete components because the wavelength becomes comparable with the physical filter element dimensions, it resulting in various losses and it severely degrading the performance of filters. To arrive at practical filters, the lumped component filters must be converted into distributed element realizations. In this section, some of the necessary tools are introduced for this conversion, namely Richards transformation, the concept of unit element, and Prudhoe's identities. Let us see Richards transformation. To accomplish the conversion between lumped and distributed circuit designs, Richards proposed a special transformation that allows open and short circuit transmission line segments to emulate the inductive and capacitive behavior of the discrete components. We recall that input impedance Zin of a short circuit transmission line of a characteristics impedance Z0 is purely reactive. That means there is no real part in this characteristics impedance. It has only that imaginary parts. That is Zin is equal to J into Z0 into tan of beta L. Beta L is the transmission line length. It will be replaced by the electric length, that is theta. So that is Zin is equal to J into Z0 into tan theta, where Zin is input impedance, Z0 is characteristics impedance, beta that is phase constant, L the length of the transmission line, and theta is the electrical length of a transmission line. Here the electric length theta can be rewritten in such a way to make frequency behavior explicit. If we pick the line length to be lambda naught by 8 at a particular reference frequency, f naught is equal to Vp divided by lambda naught, then the electric length becomes theta is equal to beta into lambda naught divided by 8. Here beta is equal to 2 pi f divided by Vp. Then lambda naught is equal to Vp divided by f naught. We can substitute these two values in this equation. We will be getting 2 pi f divided by Vp into Vp divided by 8 into f naught. Here the Vp get cancelled, then 2 divided by 8 will be getting 4 at the denominator. So pi by 4 into f divided by f naught. We can replace that f divided by f naught by uppercase of omega. That is electric length theta is equal to pi by 4 uppercase of omega, where Vp is the phase velocity and f naught is the reference frequency, beta is the phase constant, and lambda naught is the wavelength of a transmission line. Substituting equation 2 into 1, that means equation 2 is the electrical length value, that is theta is equal to pi by 4 uppercase omega. This value will be substituted in characteristics impedance Zin is equal to J into Z0 into tan theta. Here the theta is replaced by pi by 4 uppercase of omega. After that we will be getting the lumped element representation. So lumped element representation is having two components. One is inductance and another one is capacitance. For inductance, that is J into XL. XL is the reactance of inductance, is equal to J omega L is equal to J Z0 into tan of pi by 4 into F divided by F0. Here the F divided by F0 is replaced by uppercase omega. In this equation, Z0 is a characteristics impedance other than Z0. J tan of pi by 4 uppercase omega is replaced by S, because S is equal to J tan of pi by 4 uppercase omega. This is the actual Richards transformation. For a capacitance, we have to replace, that is J into BC, that is susceptance, is equal to J omega C is equal to J Y0 tan of pi by 4 uppercase omega. Here the Y0 is the admittance of a transmission line. Here also we are replacing J tan of pi by 4 uppercase omega by S. For both the equations, S is equal to J of tan pi by 4 uppercase omega. This is the actual Richards transformation. Next, the Richards transformation allows to replace lumped inductors with the short circuit stubs of a characteristics impedance Z0 equal to L. Then to replace lumped capacitors with short circuit stubs of a characteristics impedance Z0 equal to 1 by C. Finally, the choice of line length is equal to lambda naught by 8. It is interesting to note that the choice of lambda naught by 8 as a line length is somewhat arbitrary. Indeed, several authors use lambda naught divided by 4 as a basic length. However, the lambda naught by 8 is more convenient in practical filter realizations. Then, commensurate line length in Richards transformation. The Richards transformation maps the lumped element frequency response in the range of 0 less than or equal to F less than F0 into the range 0 less than or equal to F less than or equal to 4F0 due to the periodic behavior of the tangent function and the fact that all lines are F0 divided by 8 in length. This is known as commensurate line length. To obtain the inductive responses, we need to restrict the domain to 0 less than or is equal to F less than or is equal to 2F0. Because of this periodic property, the frequency response of a such filter cannot be regarded as a broadband. And the second conversion tool is the concept of unit element. First, we need to know what's the need of unit element. When converting lumped elements into transmission line section, there is a need to separate the transmission line elements spatially to achieve practically realizable configurations. This is accomplished by inserting so-called unit elements. Next, the definition of unit element. It is a basic building block or a functional component used to construct a filter, and it is used to represent the impedance transfer functions in the filter circuit. Next, unit element for a transmission line. The unit element has an electric length of theta is equal to pi by 4 into F divided by F0, and the characteristics impedance is equal to ZUE. The two-port network expression in chain parameter representation is given by this equation. It is a unit element for a two-port network. Here we are using ABCD parameters for representing the two-port network in a transmission line. That is, that unit element is equal to 1 divided by square root of 1 minus s square and determinant of 1 ZUE S divided by ZUE1. So this is the unit element for a two-port network. Here S represents the same in the Richards transformation. Then the third conversion tool is CRUDA's identities. CRUDA's identities are a set of mathematical relations used in the analysis and design of microwave filters. These identities were introduced by Tatsu CRUDA in the 1950s and have become essential tools in microwave engineering. And the CRUDA's identities are used to transform the impedance of a two-port network from one reference plane to another reference plane, allowing engineers to simplify and analyze the filter's characteristics. They are particularly useful for designing symmetrical or asymmetrical network configurations with applications in bandpass filters and impedance transformers. CRUDA has developed 4 identities to facilitate the conversion between the various transmission line realizations. The table shows the 4 types of CRUDA's identities. These 4 types of CRUDA's identities are used to replace the initial circuits. These identities are applicable for the normalized impedance of the microwave filter and allow the conversion of filter networks from one impedance level to another. They provide a powerful tool to simplify the design and analysis of microwave filters, especially when transforming between different characteristics impedances or port configurations. By using these CRUDA's identities, microwave engineers can optimize the filter design and achieve desired performance characteristics such as bandwidth, selectivity, and insertion loss. They have found the extensive applications in the development of various communication systems, radar systems, and other microwave devices. Next, let us see the design steps involved in practical filter realizations. There are 4 steps are involved in the practical filter realization. The first step, to select the normalized filter parameters to meet the design criteria. After selecting the normalized filter parameters, we have to replace the inductance and capacitance by equivalent transmission lines. After making the replacements, we have to convert series stub lines to shunt stubs through CRUDA's identities. We are having 4 types of CRUDA's identities to replace the series stub lines to shunt stub lines. The 4th step, denormalize and select equivalent microstrip lines. The selection of microstrip lines depends upon various parameters such as length, width, and dielectric constants. Specifically, the step 4 requires knowledge of the appropriate geometric dimensions of their respective microstrip lines. According to these 4 kinds of steps, we can design all the types of filters we have used in the RF transceivers. Thank you.